In section 8.2, we're looking at four things. The first is union and intersection. What are those, and how do they relate to probability? Then we're going to take a look at what the complement of an event is and how to use it to our advantage. Next, we're going to look at odds. How are they related to probability? If you know the probability, can you figure the odds, and vice versa? And then finally, we're going to look at a problem that applies some of these concepts. The union of two events is the combination of all the elements in either one of them. So the union of A or B is all of that shaded region. Another meaning for union is or, like either or. The intersection, on the other hand, is the area of elements in both A and B. Here's that shaded region. Another meaning for the intersection is the word and, like A and B. The symbol for union is this right here, and you can remember it by thinking union, and this looks like a U. The symbol for intersection is this. To find the probability of the union of A or B, you have to know the probability of A, of B, and of the intersection of A and B. Then you just add the probabilities of A and B together and subtract the probability of the intersection. Events A and B are called mutually exclusive if there is no intersection. So take a look at figure 2 and you'll see a diagram of two circles that don't have anything in common. In example 2, the problem's asking for the probability of rolling two dice and getting either a 7 or an 11. Please notice that either 7 or 11 indicates a union. So find the number of things in A, then the number of things in B, and then finally the number of things in the intersection. So now we're going to use the formula, and we find out that there are 6 plus 2 minus 0 elements in the union of A or B. Now, there's no intersection. That's why that number is 0. We know from our last class that there are 36 ways you can roll two dice. That's our sample space here. So to find the probability, we take the 8 and divide it by 36, and we get 2/9 for the probability of getting either a 7 or 11. If you take a look at figure 3, it also shows you that there's no intersection between the events A and B. Part B of example 2 is asking for the probability of rolling two dice and getting the same number on both of them, or getting a total on them that is less than 5. Once again, that or means union. So find the number of things in A, and I circle those in blue. Then in B, I circle those in red. And now the intersection are those things that have both the blue and red circle. Again, we'll use the formula, and we know that there are 6 plus 6 minus 2 elements in A or B. Why? Because the intersection has two elements this time. So that makes the number of things in A union B equal 10. To find our probability, we divide the 10 by 36, and we get 10/36, and that'll reduce down to 5/18. Either one of those is a good answer. It just depends on whether the question wants you to reduce it or not. Let's take a look at example 3. It's saying we're going to choose a random number from the values 1 to 500. And it's wanting to know what's the probability of getting a number divisible by either 3 or 4. Since it's an OR problem, once again, it's a union. That means we need to know the number of elements in A, which is divisible by 3, B, which is divisible by 4, and the intersection, which means a number divisible by both. Look at the logic here. If a number is divisible by 12, then that means it's divisible by both 3 and 4. So numbers divisible by 12 form the intersection in this problem. Then notice how they calculate how many elements are in each one of those groups. We take the number of elements in A and B and subtract the number in the intersection. We get 250. So that means the probability of the union of A and B is pretty simple now. 250 ways to get either a number divisible by 3 or 4 divided by 500, which is the number of things in the sample space. The second thing we're looking at in section 8.2 is the concept of the complement of an event. Using a Venn diagram is a really good visual way to understand this concept. The diagram is saying that if E is everything in an event, then E prime is everything outside the event. Also, if you know the probability of E, you can find the probability of its complement just by subtracting that probability from 1. It works the other way too. If you know the probability of the complement of something, you can find the probability of the original something. Now that's going to come in real handy. We're going to see that in example 4. There are times when computing the probability of an event is really long and drawn out, and it gets easier to find the probability of its complement and then use that to find the original probability. Example 4 is a good example of that. It wants us to find the probability of event E, which is that one or more of the 10 chosen parts is bad. Now the hard way to do this would be to find the probability that 1 is bad, and then find the probability that 2 are bad and add that to the first probability you got. And then find the probability that 3 are bad and add all of those together and just keep on going. That would involve 10 separate calculations. One thing you have to realize is that the opposite of at least one bad is that none of them are bad. So let's find the probability that none of them are bad. Again, that's the complement of at least one bad one. And then we'll subtract that probability from 1. So we let E prime be the event that none are bad. How do we find its probability? We know that there's a shipment of 45 parts and 9 of them are bad. That means 36 of them are good. So the number of things in E prime, that is the complement of E, is 36. Think about that. There are no bad ones in E prime. How many ways could we choose 10 good ones out of 36 good ones? Right, we use the complement function 36 complement 10, meaning 10 things chosen out of 36. And how many ways could we choose 10 things from 45? Well, 45 complement 10, meaning 10 things chosen out of 45. We're using the complement function because the order doesn't matter. Now we divide those two to get the probability of E prime and get the answer to 6 decimal places. For this problem, we'll just round it to 2 decimal places like the book did. Remember, though, that we found the probability of the complement of what we really want. So we have to subtract that complement's probability from 1 to get our actual answer. Said in other words, the probability that the shipment will be refused because 1 or more of those items are bad out of the 10 sampled is about 0.92. That's a really high probability when you consider that the highest a probability can get is 1. The third thing we're taking a look at is the concept of odds. Now this comes up quite a bit in games of chance like gambling. For instance, the odds of winning are 3 to 1, those sort of things. So let's say the probability of winning is 3/8. To find the odds of winning, keep the 3 on top and then subtract it from the 8 to get 5. That means the odds in favor of winning are 3 to 5, and we can write it as a ratio 3:5. The odds against winning are 5 to 3. In other words, the numbers are just flipped. Take a look at what I've got circled in this green highlighter. Make sure you understand what it's saying. So if we go back to our example, it means this. Okay, let's turn things around. Let's say I know the odds. How would I find the probability? If you know the odds in favor of something, you take that left-hand number and put it on top of a fraction. Then you add the two values together, here the 5 and the 3, to get the bottom number. Doing that, we get our original probability back. Finally, let's take a look at a practical application. Pause for a second to look at the concept of the law of large numbers. It says that if you repeat an experiment like rolling dice or flipping coins or whatever, the probabilities that you observe get closer and closer to the true probability of an event. It just takes a whole bunch of times doing that experiment. And this idea of the law of large numbers is one of the bases for statistics and a bunch of other math. Looking at example 8, let's translate that to a Venn diagram. In a Venn diagram, the rectangle represents the entire sample space. So here, the rectangle represents a sample space of 1,000 people. And we're going to draw one person randomly from that 1,000. The circles represent the diet cola drinkers and the regular cola drinkers. In this problem, there's an overlap, meaning an intersection, because some of these 1,000 people drink both diet and regular cola. Now, when you're putting numbers in a Venn diagram, make sure you start with the inner part first, where the overlap is, where the intersection is. So I put 200 drank both. Now I know that 300 goes here. Why? Because I know that the total of diet drinkers is 500. So the 300 plus the 200 in the intersection are all diet drinkers, right? And now I can put 400 here because the total regular drinkers is 600. That means outside of the circles, I have to put 100. That 100 must be the people who drank neither diet nor regular cola. Okay, so we've got our diagram. Part A of this example says, what's the probability that a randomly chosen person tried either diet cola or regular cola? Because of that or, it's a union. So the number in the diet cola circle is 500, plus the number in the regular cola is 600, minus the number in the intersection, which is 200. All of that is going to be divided by 1,000, the number of people in the sample space. So the probability for part A is 9/10, and you can write that as a decimal or a fraction. That means the odds in favor of the event are 9-1. Part B is asking for the probability that the chosen person tried one of the colas, but not both. We look at our Venn diagram again. Here's where it really starts coming in handy. I can see that the number who tried diet, but not regular, is 300. And the number who tried regular, but not diet, is 400. So the probability is going to be 700 divided by 1,000, which is 7/10. Now I wrote down the odds in favor of that, 7-3. But I messed up. The question is asking for the odds against. So I have to flip the values like this. I hope this video helps you when you're trying to work the problems in this section. But if you run into something that doesn't make sense, make sure you email me. Thanks for watching, y'all.